In this lecture, we'll look at JS prototypes, which hold properties that are common to all objects of a JS class, like string or number. Now, in the example code, in the diagram here, we start by modifying functions in a library object, the way we did in the last lectures of the objects topic. On line 4 here, we replace string x's toUpperCase function with an alternative that simply says return x is uppercase, and then we use it on line 6 here as the output demonstrates. On line 5, we introduce a standard function of all objects, hasOwn property. Now this is passed a property name, like toUpperCase, and it returns true if that property is present in the object, and the output from it confirms that toUpperCase is a property in X. Now, on line 8, we delete X's toUpperCase function. At this point, having displaced the original toUpperCase and then deleted its replacement, we might expect that X's toUpperCase property would be undefined. But the call on line 9 instead shows that the original toUpperCase is back. And yet the call on line 10 of x.hasOwn property now shows false, indicating that toUpperCase is not present in X. So what's going on here? Well, down below is a diagram of what happened. And you don't have to understand the entire thing just yet. In fact, I've blanked out the top part for now so that it's not distracting. We'll look at that in a little bit. The fact that we're missing here is that every object has a property called __proto__. And this points to another object that is the first object's prototype. The prototype acts as a backup object or a default object. If we attempt to access a property, either function or data, that is not present in an object, then the object defers our request to its prototype. And if the prototype has the property, then the prototype's property is used as a backup. And all objects created by a given constructor, for instance, all string objects, share a common prototype object, unless you take special action to change that. So in the diagram, we show the string targets of x and of y pointing to the same prototype object, which prototype object we label string prototype. In fact, none of our string objects has ever had a toUpperCase method unless we hand added it like we did on line 4. It is the shared string prototype that has this method, and all our uses of the method thus far have been deferred to the prototype, except for that brief moment when we had an overridden one for x. If we give an object its own version of a property, like we did for x.toUpperCase, then that takes precedence over the prototype's version, as we saw on line 6, and as shown by the dashed line arrow from x's target to the toUpperCase alternate 1 function, which shows the situation that was in effect from line 4 to line 8 of the code when we temporarily replaced x's toUpperCase function. But the prototype is still waiting there in the background, waiting to take over again if the object's property is deleted, as we saw on line 9. So here's a quick in-lecture question. Based on what we've seen so far, what statement would you need to make to actually be undefined and result in a runtime error? And that's without changing x itself. Well, returning from a pause, you'd need to delete x.proto.toUpperCase. And now you've killed the main instance of toUpperCase, and there will be nothing to fall back on. Question 2, if you did that, would quote hello, quote, using a literal string, .toUpperCase still work? Again, after a pause, no, you'd be calling the toUpperCase method on a temporary wrapper object, a string wrapper object, and that wrapper object would share the same toUpperCase deprived prototype as all the other string objects. Once you've modified the prototype for one string, you've modified it for all of them. Now, these last two questions are not just academic. They show that it is possible to dynamically modify the prototypes themselves and thus affect all objects of the type. Let's look more closely at that. On line 12 up here, we replace the string prototype's toUpperCase property. The diagram shows the original toUpperCase property now replaced by our alternative right there. Now, as the output of lines 13 and 14 then show, both x and y now have altered toUpperCase behavior since they both defer to their prototype. And as line 17's output here, there, also shows, even a new string z sees this change because all objects created by the string constructor share the same prototype. Now, prototypes let you standardize all objects created by a constructor, providing one shared copy of all the functions without having to make them properties of every object. All that's necessary is to correctly set the proto property of each constructed object. How does each new object's proto property get initialized? Well, as the diagram again shows down here, the string constructor function includes a property called prototype, referring to the shared prototype. Most constructor functions supply such a property, and if it exists, the new operation automatically copies the constructor's prototype into the proto property of the new object. Now, the name of this constructor property is rather confusing. It should have been named model prototype or some such, and the proto property should probably have been called prototype. Apparently, the early JS design didn't anticipate that people would want to directly access the proto property, and that's why it has an odd name. But as with other JS oddities, we're stuck with it now. So, to summarize, the __proto__ is a reference that every object has pointing to its prototype. The prototype property is a reference in constructor functions, and it's used to set up the proto of any object they construct. Be sure you understand that both equality checks, for instance, on line 19 up here, are true, per the discussion we just had. Now, you don't have to use an object's proto property to modify the shared prototype. You can use the constructor's prototype property to do so, as on line 21 here, where we add a onemore function property to number.prototype. This function returns its context object +1. Now, all numbers now have this function via their prototype, and so do elemental numbers by virtue of being wrapped in a number object. So on line 23, for instance, we can call onemore on number I and on the constant 42 and get the expected output of 2 and 43, as you can see. Question 3. Would swapping lines 21 and 22, putting the construction of I first, have changed the output of line 23? After a pause there, no. Even existing number objects will see the onemore property since they all share the same prototype, onemore to the number prototype. So I would have the onemore property in its prototype even if we created it before line 21. You can spontaneously add a function to all existing objects of a class by modifying the prototype, and it's not uncommon for JS code to do so. Now, to complete the circle of references, each object is also given by the new operation, a property constructor, which refers back to the constructor function that initialized the object, as shown here in the diagram. So both equalities in the constructor check from lines 25 and 26 are also true. Generally, obj.constructor.prototype is a synonym for obj.proto, assuming you haven't done something drastic like changing the proto property after construction. Now, we said earlier that all objects have a has-own property method, but using that method to check for its own presence, as on line 29 here, produces false, as you can see in the output up here. Now, that really shouldn't be a surprise, though, by now. X, or has-own property, is probably in X's prototype. But when we check that down here on line 30, we again find that it's false. The further detail that's missing here is that prototypes also have a proto property. They're objects after all, and again, all objects have a proto property. So if a prototype lacks a property, it in turn refers to its own prototype. Let's remove this blacked out box here to show the entire diagram. And we can see that the check on line 31 here reaches all the way x.proto, all the way up to X's grand prototype, so to speak. And we find that the has-own property is there. Now that grand prototype is the object prototype, because that is string prototype's parent prototype. String, like other JS built-in types, is derived from object. We'll look closely, or more closely, at what derived means in JS in the next lecture. But from the diagram, it apparently involves the derived class's prototype pointing to the base class prototype as its own proto. So where does this prototype chain stop? Is there an x.proto.proto.proto? Is it turtles all the way up, or does the recursion end somewhere? It stops with the object prototype, which is sort of the granddaddy prototype object. This is where has-own property and various other universally applicable functions are found. And object.prototype.proto is null, as the diagram shows, so the buck stops there. Question 4, is this the first time in this particular program that chain of references, x.proto.proto, has been traversed? And if not, then what other line or lines of code followed it? Turn from a pause. Well, any call of x.hasOwn property must have followed it in order to find the hasOwn property function in order to call it. So line 29 followed that reference path. And there's one final point worth noting in the diagram. It was only recently that JS added a method that lets one easily list all the properties that are present directly within an object, not in its prototype chain. And this is object.getOwnProperties, or own property names, I'm sorry. And it's called, but commented out in the example code here, since not all JS interpreters can presently handle it. It takes an object as a parameter and returns an array of strings giving all property names present in the object. And you call it like this, object.getOwnPropertyNames. Question 5, in the diagram, getOwnPropertyNames is a property of the object constructor, not of the object prototype. Why does that make sense? Coming back from a pause there, well, if it were callable on objects as a method, like hasOwn property, then we'd expect it to be a property of object prototype. But since it's static, it's called as object.getOwnPropertyNames, then we expect it in the object constructor. Prototypes, in effect, contain only non-static functions.